This is my Calculus 1 course. Today we're going to learn about higher derivatives, the second derivative test, concavity, and inflection points. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So here's the differentiation formulas. We're going to be using these today as we do in most classes in this course, but I just want to have these for you in case you forget some of these lesser known formulas, like the ones down here or here. You may need those. They're not really used that often. Some of those I highlighted are not used very often, so you may need those to remind you how to find the derivative of those functions. And we also have the derivatives of the trigonometric functions. So get a picture of these. And now we're going to learn about higher derivatives. So we learned how to find f prime, the derivative of a function, and in the previous class we had a test called the first derivative test, and you probably wondered, why are we calling it the first derivative test? The reason we call it the first derivative test is because there's actually a second derivative test. And not only is there a second derivative, but there's also something that we call f triple prime and f quadruple prime, and these are what we know as higher derivatives. So in this problem, we're going to find f double prime and f triple prime, the second and the third derivative. Now, the first derivative, f prime, which we'll go ahead and find, for this particular function, f prime is negative 24x squared plus 2. The exponent comes down, is multiplied into 8, and the new exponent is one less than the old exponent. So that is the first derivative. That is the rate that the y values of the points of this graph are changing as x changes. How fast are the y values changing as x changes? But the second derivative is how fast the rate of change of the y values are changing as x changes. It gets kind of complicated. One way to think about it is if you were to graph this function. I don't know what the graph would look like. We could graph it if we really wanted to, but I don't really want to do that now. But let's say we graphed this function and it looked like that. If you find the derivative at some x value, let's say you plug in x equals 1, then the derivative is the slope of the line that's tangent to the graph at that point. The double derivative is how fast the slope of this line is changing at that point. So the double derivative is the rate of change of the rate of change of the y values of the function. It's kind of, again, it's kind of complicated. The triple derivative is the rate that the rate of change of the y values is changing. Again, it's very, very complicated. In calculus, you're really only going to use the first derivative and the second derivative. The third and fourth and any derivative above that, they're not really used for much in the calculus curriculum. But you are going to be expected to know how to find higher derivatives like the third or fourth or fifth or sixth derivative. So again, the double derivative or the second derivative, whatever you want to call it, f double prime, that's how fast the slope of this line is changing as x changes. Whereas this first derivative is just the slope of the line. The double derivative is how fast the slope of the blue line is changing. So when you find higher derivatives, you're just finding rates of change of rates of change. How fast are the actual rates changing? So let's find the double derivative, f double prime. To find f double prime, you simply find the derivative of the derivative, and that's negative 48x. So it's that simple. F triple prime is the derivative of the second derivative, so that's just negative 48. So the good news is that this really is not difficult. Okay. Let's try number 2. So notice that we are now using Roman numerals. When you go to higher derivatives, it's convenient to use Roman numerals. So this is the fourth derivative. In order to find the fourth derivative, we need to find the first derivative, and the first derivative is going to be 1/2 sine x. That becomes 0. We're using the constant multiple rule. We have a constant times a function. The derivative of that is just the constant times whatever the derivative of the function is. The derivative of the function is negative sine x. So negative sine x times 1/2 is negative 1/2 sine x. This is all stuff that you should know really, really well by now, because we've done plenty of these problems. Now we're going to find the derivative of the derivative. That's the second derivative. So that would just be negative 1/2 cosine x. Again, we use the constant multiple rule. Now, if you forgot the derivatives of your trigonometric functions, you're going to need those. So please take a picture of these. Okay, so now we're going to find the triple derivative. We're going to take the derivative of the double derivative. We're going to find the derivative of the second derivative, and that's going to be 1/2 sine x. So you see how the sign keeps changing. Well, it's not changing every time, but maybe every other time it'll change. So now we're going to find the derivative we're actually looking for. We had to first find those derivatives. Now we're looking for the fourth derivative. That's just going to be 1/2 cosine x. So we have one of our answers. We're also looking for the sixth derivative, but we can't do that unless we find the first derivative first. So that's going to be negative 1/2 sine x. And then we can go to the sixth derivative. That's negative 1/2 cosine x. So as you can see, this is really not difficult. You're just finding the derivative over and over and over and over again. And so let's double check this, make sure we did it right. Everything looks good. So let's try a couple more of these problems. Again, as you can see, this is really not difficult. We're looking for f double prime and the fifth derivative. So the second derivative and the fifth derivative. Now, if you recall, the derivative of natural log x is 1 over x. So now we're going to find the derivative of the derivative. And before we do that, it's useful to change to x to the negative 1 power. You can also use the quotient rule. But students really don't want to use the quotient rule because it requires more thought. So oftentimes students just want to use negative exponents rather than the quotient rule. So then we use the power rule, so we have the double derivative, and I guess we can change that into a form that we can actually understand. That's what that actually means. And then we're going to find f triple prime, not because we're looking for f triple prime, but because we need to find that in order to get to the fifth derivative. Now we're looking for f quadruple prime. And finally, we're going to get the fifth derivative. Using the constant multiple rule and the power rule, we end up with the following. And then of course we can change the form of that into something that we can actually understand. So there you go. Now again, if you want to use the quotient rule, that's completely fine, but the quotient rule gets really, it's just a lot more work to have to do that. In calculus, you can avoid the quotient rule quite a bit. In fact, you can avoid it in just about every situation. There's just a few places where you may not be able to avoid it. Okay, so let's try another one of these before you try one on your own. So just one more. So we're looking for the 10th derivative. So let's first find f prime of x. Now don't be fooled by this green term here. Students are going to be tempted to take that 2 and throw it down in front using the power rule, but this is just one big constant, so that just becomes 0. So all of that just became 0. That was kind of a trick problem. Now f double prime, and by the way, the derivative of e to the x is e to the x. Do you remember that? That's the only function where if you find the derivative, it's actually the same function. So if you find f double prime, that's just going to be e to the x. If you find f triple prime, that's just going to be e to the x again. You keep finding the derivative, it's just the same function. So what that means is that when you get to the 10th derivative, obviously that's just going to be e to the x. So again, these are called higher derivatives. Now I want you to get a picture. I'm going to give you one more chance to get a picture of all these formulas here and a picture of these problems that we just did together. And I want you to try number 5. Find the second derivative and the third derivative. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 6. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, go ahead and try number 7. Now for number 7, you're going to have to use the exponent rule, or the rule for exponential functions. So try your best on number 7. When you come back, we'll do it together. Okay, we're back. Let's double check all that, make sure it's correct, everything looks right. So if you got that right, excellent. Go ahead and try number 8. When you come back, we'll do it together. Okay, we're back. Okay, so again, if you got that right, excellent. So those are higher derivatives. You're going to be expected to know how to find f triple prime or f quadruple prime, the third derivative, the fourth derivative, the fifth derivative, but the reality is you're really not going to use those derivatives. You're only going to use the first derivative and the second derivative 99.999% of the time in your calculus curriculum. Now, I want you to know that these problems can get a lot harder. We're not going to go into more difficult problems because all you're doing is just finding the derivative over and over again. We've already done that, but we'll just do a couple problems that will show you that this type of problem can actually get much more difficult. So we're looking for f double prime. Now f prime we know is negative cosecant x times cotangent x. Why? Because that's one of our derivative formulas. That's this one here. So are you supposed to remember that? Yes, you're supposed to have that memorized. But now, what if we want to find f double prime? Well, this presents a problem, because now we have the product of two things, a blue thing and a green thing. When you have the product of two things that are actually functions, then you have to use the product rule. And students don't want to use the product rule, and they don't want to use the quotient rule. They don't like using those, and they don't like using the chain rule. There's all kinds of rules that students don't like using in calculus, the big ones being the product, the quotient, and the chain rule. They don't want to use those. They try to avoid using those, and this is a situation where students will look at that and say, well, I don't want to do that. Unfortunately, you have to use these rules over and over and over again in the calculus curriculum. You can't avoid it. So you can do this in different ways, but I'm going to consider f of x to be negative cosecant x, and I'm going to consider cotangent x to be g of x. And you really should know how to use the product rule by now. But I'm just going to show you how to do this using d over dx. You don't have to write d over dx, but I'm going to go slow here just so you can review the product rule. So we found this stuff up here. So that's f prime, and g of x, that's that. And if I can find some different colors here, f, that's the first function, which is negative cosecant x. And maybe we'll use red for this last one. That's going to be the derivative of cotangent, which is negative cosecant squared x. Okay. So actually I forgot to use my d over dx notation. So we're finding the derivative of cotangent x, and you don't need brackets like you needed over here because there's no confusion about what you're finding the derivative of. Okay, so you can see that this is taking a lot longer than it really needs to take. That's because I'm showing the steps. You don't have to show this d over dx stuff. You can just find the derivative. If you know how to use this rule, then just use it. Just get it over with. Okay, so now the derivative of negative cosecant x is negative, actually it would be positive cosecant x cotangent x, because the negative, well, double negative turns to a positive. So all that became that, and of course this stays that. We have negative cosecant x, that stays. The derivative of cotangent is, as I mentioned, negative cosecant squared x. So now we can combine a lot of this into exponential notation. And there you go. So there's a good possibility that you could simplify this by using trigonometric identities, but that's not really the point of this, to mess with trigonometric identities right now. The point is just to learn how to find the second derivative. So I want you to try a problem like that. Again, we're not going to we're not going to do a lot of these. I'm just showing you that some of these problems can get pretty involved. So try number 10. If you want to take a picture of the trigonometric formulas again, you can do that. Try number 10. When you come back, we'll do it together. Okay, we're back. The point of this is not to get you bogged down with a bunch of tedious problems. The point of this is just to show you that, again, some of these problems can get involved. So now we understand the concept of the second derivative, or we at least know how to find it. And that brings us to the next thing we're going to study in the class today, and that is what we call the second derivative test. Again, in the previous class, we learned the first derivative test. Now let's review. What was the first derivative test? What did that tell us? In fact, I'm going to show you the first derivative test just so you remember what it was. What was the point of that test? The point was to test a function at the critical numbers to determine whether or not you have a maximum or minimum value of the function at those critical numbers. Remember, the critical numbers are the places where the maximum values or the minimum values are going to occur. It's like if you're looking for fish, you need to find where there's water. The fish are going to be in the water. Now, just because there's water doesn't mean there's going to be fish. It doesn't prove that there's fish, but if there are going to be fish, then there's going to be water. So the critical numbers are the water. That's where the maximum or minimum values of a function could occur. So we found critical numbers, and remember, we found critical numbers by finding where the derivative is 0 or undefined. We found the critical numbers, and then we tested the function at the critical numbers. And the first derivative test told us whether or not we had a maximum value or minimum value or neither at the critical numbers. So did we have fish or did we not have fish? Where the water was. Now here's something very important to understand. The second derivative test, which is what we're going to learn today, the second derivative test does the same exact thing that the first derivative test tells us. The second derivative test does the same thing that the first derivative test does. It just tests functions at critical numbers to determine whether or not we have a maximum value or a minimum value. So even though it's called the second derivative test, even though we're using the second derivative, not the first derivative, this test does the same thing. We're just trying to determine if we have a maximum or minimum value. So it's like if you're going to test a rock. Let's say you're a geologist and you're going to test a rock. There's many different ways that you can test that rock, but the tests are all trying to do the same thing. They're all trying to figure out what type of mineral you have. The first and the second derivative test, they all do the same thing. They're trying to figure out, do you have a maximum value of the function or a minimum value of the function? They do this, the tests both do the same thing. They're just different ways of testing the function. So, for example, the first derivative test might be a scratch test. You scratch the rock to see, how it can be affected. I think it's called the hardness test. I don't know. It's been a while since I took geology. But there's also tests. There's other tests that you can do on the rock. You can put some acid on the rock, and how it responds to acid, that helps you determine what type of mineral it is. So the acid test might be the second derivative test. The scratch test might be the first derivative test. They're both trying to figure out what type of mineral it is, but they're different ways of testing. So again, the first and the second derivative test, they're both trying to figure out what type of mineral it is, but they're different ways of doing it. So the first and second derivative test are both trying to figure out if you have a maximum or minimum value of the function, but they're doing it in different ways. So you can take a picture of this. This is just up here, a review of what a critical number is. And down here, this is the actual second derivative test. So get a picture of this information. And now we're going to learn how to use the second derivative test. Now you might wonder, why do we have to use the second derivative test? Why don't we just use the first derivative test? In all honesty, the first derivative test is actually used more commonly simply because it makes it to where you don't have to do the work to find the second derivative test, because in order to find the second, or in order to use the second derivative test, you have to first find the first derivative. Because in order to use the second derivative test, you have to find the second derivative, but in order to do that, you have to find the first derivative, so it's more work. In general, we don't really use the second derivative test that often, we just use the first one. But there are situations where the second derivative test is actually going to be required. And this is especially true for the advanced placement calculus exam. There are going to be situations where they want you to use the second derivative test. And it's actually may not even be possible to use the first derivative test. So we're going to find the x values where the local maxima and minima of each function occur, just like we did in the previous class. But now we're going to use the second derivative to test, to verify that the x values that we find, the critical numbers, are indeed the locations of extrema, because sometimes, you know, they're not the locations of extrema. For example, if you have a graph that looks like this, well, this x value is a critical number, but this is not a, this y value at this point is not a maximum or minimum value. And we're also going to use the second derivative test to distinguish between maxima and minima, as we talked about previously. So let's do a problem here. So we want to know where the maxima and minima are of this function. Where's the maximum values and the minimum values? And so remember, if you're looking for fish, where do you first look? Water. The water is the critical numbers. So what are the critical numbers? The critical numbers are where the derivative is equal to 0. Well, in order to figure that out, we first have to find where, or we have to first find the derivative. Then we set it equal to 0. Then we solve. And then we have our critical numbers. So in this problem, we have to solve an equation with a cube, but this is just basic algebra. Shouldn't be a problem. So we have x is equal to 0. So if you put the 8 on the other side and then cube root both sides, you get x is equal to -2. So we found the critical numbers. Now we're going to use the second derivative test. But we can't use the second derivative test unless we first find the second derivative, of course. Now we have the first derivative over here. Remember, the second derivative is just the derivative of the first derivative. And that's going to be 20x cubed plus 40. So now that we have the second derivative, we can use the second derivative test. So I'm going to bring that second derivative down. And let me show you how the second derivative works, the second derivative test. When we use the first derivative test, let's say that this function looks like this. I don't know what it really looks like. That's this function here. We tried to find maximum and minimum values by first finding the critical numbers. Remember, that's where the water is. If you're looking for fish, you have to look where the water is. So the critical numbers are where the water is. Then we tested the function at these critical numbers by finding the slope of the line that's tangent to the graph to the left of that purple point, and we found it was a positive slope. The slope was a positive number. Then we found the slope of the tangent line, the slope of the line that's tangent to the graph to the right of that point, and we found that the slope is negative. So the slope changed from positive to negative as our x values progressed across this point. So that showed that we have a maximum value of the function. And again, the slope of the tangent line is the derivative. And we did something similar down here to show that we had a minimum value of the function. The y value of this point is a maximum value. The y value of this point over here is a minimum value of the function. That's the first derivative test. But now we're going to use the second derivative test. So the second derivative test is really easy. All we have to do is evaluate the second derivative at the critical numbers. And if we get a positive number, which is what we got in this case, then that tells us that there's a local minimum value at x equals 0. So I already wrote that down there. At x equals 0, there's a local minimum value. Now it could be the absolute minimum, but remember, an absolute minimum is always called a local minimum also. It qualifies as a local minimum, and as long as you're not talking about endpoints. So this would be an absolute maximum, for example, and this would be an absolute minimum, but they're not local because they're endpoints. That's just the way that the books define it. Now this would be an absolute maximum, but it would also be a local maximum. And of course this would be an absolute minimum, and it would also be a local minimum. I know it's kind of annoying having to remember all those weird definitions. Now let's evaluate let's evaluate the double derivative, f double prime, at the other critical number. And it looks like we get negative 120. I did that kind of quickly, so let's double check. It looks right. So that number is a negative number, right? So if we evaluate the double derivative at a critical number and we get a negative number, then that means there's a local maximum value of the function at x is equal to negative 2. So that's it. That's how you use the second derivative test, so it's very easy. Now, I want to talk a little bit about why this test works. This will help you remember the test. So let's say that you have a graph that looks like that. So if you plug in this x value, here's another x value. Those are the critical numbers, obviously. You plug in the x value to the second derivative, and if it's positive, if the second derivative, when you evaluate it at this x value and the second derivative is positive, then that means that the y value at this point is a local minimum. But why is that? Well, look at what's happening to the tangent lines as x gets bigger and bigger around this area. So you have a tangent line with a negative slope, and then the tangent line has a bigger slope. It's still negative, and then the tangent line has a bigger slope, so the slope of the tangent lines are increasing, and finally they become positive, and so on and so forth. So the second derivative is the rate of change of the slope, and if you have a minimum value, then the slope is going to be getting bigger and bigger, so the second derivative is going to be positive. So that's why if the second derivative is positive at this critical number, then this is a minimum value. And the same thing is true, the same type of logic is true if the slope of the tangent line is getting smaller and smaller as x increases around this area, then that means you have a maximum value. So the rate that the slope is changing is actually negative. So that's why when you evaluate the second derivative at this critical number, the second derivative should be negative. And that's what I use, personally, that's what I use to remember this, this derivative test. Now, it's important to understand that well, f double prime has to exist near the critical number. If it doesn't exist, then the test doesn't really do anything. Also, if the double derivative is 0 at the critical number, the test produces no useful results. So the second derivative test only works when the double derivative is actually defined, or if it's a non-zero number. Notice down here it says undetermined at. That's what you fill out when you have the situation where the double derivative is 0 or undefined. Okay, so let's go on another problem here. As you can see, the second derivative test is really easy. It's really not difficult at all. So let's go a little faster now. So we're trying to find maximum and minimum values of the function, right? So it's like looking for fish, but where do you look for fish? You look for fish in the water. The water is the critical numbers. So we have to find the critical numbers first. What are critical numbers? Critical numbers are numbers where the derivative is 0 or undefined. So we're going to find the derivative, which is what we just did, and then we're going to set it equal to 0. There's no x values that make this function or the previous function that we did undefined, so we don't have to worry about where it's undefined. And if we have a situation where the derivative is undefined at some x value, then most likely the second derivative test is it's not going to work. So those problems don't really apply here. In those situations, we'd have to use the first derivative test. So I'm going to solve this equation to find the critical numbers. And we found them. X equals -3. That's the critical number. So that's the number that makes the derivative equal to 0. So now that we found water, we're going to see if there's any fish in the water, the maximum and minimum values. But we're going to use the second derivative test rather than the first derivative test. In order to do that, we have to find the second derivative. We haven't found the second derivative yet. We've only found the first derivative. The second derivative is the derivative of the derivative. So now we have the second derivative, and we can bring that down here and use it to perform the second derivative test. Alright, so how does it work? Well, it's very, very easy. We just evaluate the second derivative at the critical number. plug it in, and we see what the sign is. So we get negative 18 plus 18, which is 0. So over here, if we evaluated the second derivative at a critical number and we got a positive number, that meant that the critical number led us to a minimum value of the function. If we evaluated the double derivative at a critical number and we got a negative number, then that critical number led us to an x value where the function is where the function has a maximum value. But what if it equals 0? In that case, the second derivative test doesn't do anything for us. The function, it's undetermined whether or not the function has a max or a min. So instead we write undetermined at x equals 0. So what do? Well, we go to the first derivative test. See here it says if f double prime equals 0 or it doesn't exist, then the test produces no useful results and the first derivative test must be used instead. Now we're not going to do that. We're not going to use the first derivative test. We could, it wouldn't take very long, but in fact maybe we should just go ahead and do that. We have plenty of room here. So remember, the first derivative test is just testing or checking the sign of the derivative around the critical number. So let's use the first derivative test. And in order to do that, we have to use the first derivative, of course. So let's bring that down. We already found that. So remember, how it works is you have a sign chart, and it's going to be really easy for this problem because we only have one critical number. And then we just check the sign of the function. So, or the sign of the derivative, that is. So we're going to plug in -3, or a number around -3, that is. So let's try -4. And looks like we get 48 minus 72 plus 27. And that leads us to, looks like 3. So that's going to be a positive number. And then we have to check the derivative to the right of that critical number. Let's try 0. That's an easy number to plug in. And we see we get a positive number, which is 27. So basically what that means, because the sign didn't change, we don't have a maximum or minimum value at that critical number. So I'm not going to make you use the first derivative test in this class because that just makes the class go a lot longer. Now we can conclude no max or min. So that's basically the answer. All right, so let's do another one of these problems. I'm not going to make you use the first derivative test because it's going to take away time from using the second derivative test. So we're going to use the second derivative test to find the maximum and minimum values. But again, remember, if you're looking for fish, you need to look for the water. The water is the critical numbers. So to find the critical numbers, we find the derivative, and then we set it equal to 0. And we solve the equation. And it looks like we have the difference of two squares. So we're going to have to factor that. And so one critical number is 0. Another critical number is 5/2. And another critical number is -5/2. Okay. So now we're going to test the function at these critical numbers to see if we have maximum or minimum values using the second derivative test. Problem is we can't use the second derivative test unless we first find the second derivative. So let's go up here and look at the first derivative, and we'll find the derivative of the first derivative, and we get 12x squared minus 25. So now that we have the second derivative, we'll bring that down and use it to perform the second derivative test. So the way that the test works, it's really easy. We just evaluate the second derivative at the critical numbers. So first we'll plug in 0. Where did I get 0? That's up here. That's a critical number. And you notice we got a negative number. So what does that mean? It means that there's a local maximum at x equals 0. Now we'll evaluate the double derivative at 5/2. So we're plugging in this critical number here. And it looks like we get 50. So that number is positive. So if the double derivative is positive, that means we have a local minimum at x is equal to 5/2. We have one more critical number, a green critical number. So plug in -5/2. And looks like we get the same number. So looks like we have a another minimum. So we can put comma -5/2. So we found the locations of maximum and minimum values of the function. And again, that's the original function. We found the locations of the maximum and minimum values, and we identified which location gives what type of value, a minimum or a maximum, using the second derivative test. So that's it. As you can see, the test is really not difficult, and it shouldn't be very difficult to remember how to use the test either. It's not that complicated. The good thing about calculus is that most of the the math, the calculus itself is actually not the hard part. The hard part is the algebra. That's typically what students have trouble with. Okay, so let's do one more of these problems together before we try one on our own. So we're going to find the maximum and minimum values, or we're going to find where they are, and we're going to identify which locations lead to a maximum and which locations lead to a minimum. So again, if you're looking for fish, where do you look? The water. The water is the critical numbers. So before we find the critical numbers, we have to find the derivative, because the critical numbers are where the derivative is 0 or undefined. But before we find the derivative, we're going to change to exponential notation because it's just easier to find the derivative that way. So we have 1 minus 1/3 times x minus 4 to the negative 2/3 power. And then of course we multiply by the derivative of the inside if we wanted to use the chain rule. But we don't have to do that because the derivative of the inside is just 1. You could put a 1 out here if you wanted to, but it's not really necessary. So that's f prime. So I'm going to change back to root notation so we actually know what this expression even means. Okay, so we want to know where f prime is either undefined or 0. That's the critical numbers. So I'm not going to do a lot of this math. Well, maybe I'll just do it. I'm going to change 1 to 1 over 1, and I'm going to get a common denominator. We have to combine everything to one expression. It is possible to find critical numbers without combining these terms into one expression, but it's easier to see the critical numbers if you just combine everything. We can see that x equals 4 is a critical number because this expression is undefined when you have that x value plugged in. So we can already see one critical number. But to make things easy for us to see, it's better to combine everything to one expression. So I'm going to get a common denominator. You should know how to do this on your own. Calculus teachers are going to expect you to be able to do this on your own. Get a common denominator, combine these expressions into one expression. But I'm just going to show you just so you remember how to do this. Well, now we have a common denominator, so we combine everything and we end up with the following. Okay, so now that expression helps us to find the critical numbers. Where is this? Where's the derivative 0? What x value is going to make the derivative 0? Well, that's whatever x value is going to make the numerator 0, but not the denominator 0. So I'm going to set the numerator equal to 0 and then solve it. But we have critical numbers if the x value makes the denominator 0, but not the numerator 0. So we can see pretty clearly that x equals 4 is going to make this expression 0. You can do all the math on that if you want to. You just divide by 3 to get rid of that. Cube both sides of the equation to get rid of this, and then square root both sides of the equation to get rid of that, and then add 4 to both sides of the equation. But that would just take forever. It's not really necessary to do that. You can see what x value is going to make that equal to 0. Here we're going to add 1 to both sides of the equation. You don't have to show all this math. but we're going to add 1 to both sides. We're going to divide both sides by 3. So we're isolating the root expression. So then we're going to cube both sides of the equation. We get 1 over 27. So as you can see, we're kind of out of room. So I'm going to bring this up here. Remember, if you run out of room, don't panic. So now we're going to square root both sides and add 4 to both sides. So this is where things get really tedious, when you have to deal with stuff like this. But you can't avoid it. You're going to see this stuff in the calculus curriculum. It's coming for you. You can't avoid tedious problems in the calculus curriculum. I wish I could protect you from that, but I just can't. They're going to come. Okay, so what we should do is go ahead and calculate, because we don't want to have to carry that expression around with us. So let's get our calculators, and we're going to enter 1 divided by 27, then equals button, and then square root of that, and then plus 4. And it just depends on what kind of calculator you're using. So I got that for x, or let's see what else we get. I got 3.8075. Okay, so now we're going to perform the second derivative test. So we just need to evaluate the second derivative at those critical numbers. Well, we don't have the second derivative, so we can't do that. So first we have to find the second derivative. This is the first derivative, and to find the second derivative, it's going to be easier to use this expression probably. So we have 0, the derivative of 1 is 0, and then we're going to use the exponent rule, and we're going to bring that negative 2/3 down. That's going to become positive 2/9. X minus 4 to the negative 5/3 power. Okay, so let's put that double derivative in a form that we can understand. We'll end up with the cube root of x minus 4 to the 5th power. So that is the double derivative, and we need to evaluate that at the critical numbers. But as you can see, this is not going to be very easy, because this is really tedious math. So this is where your calculator is really going to come in. First of all, let's copy the double derivative, or f double prime, the second derivative. We'll put that here. And we need to evaluate that at the critical numbers. So one critical number is 4 plus the square root of 1 over 27. If we're going to use our calculators, then it might be better to just write the actual number. So I don't know if we really need these red abbreviations. Then f double prime at 4 minus root 1 over 27. So So before we forget, let's remember this critical number here. We can see that if you plug that critical number into the double derivative, it actually makes the double derivative undefined. So that means that the second derivative test doesn't really help us. So it's undetermined at x equals 4 whether or not the function has a maximum or minimum value or any extrema. So at that point, we'd have to use the first derivative test. But again, you don't have to use the first derivative test. We did that on a previous problem, but it's not really. I'm not going to require you to do that. So now we have to calculate these values here, and rather than use these estimations here, these approximations, you can probably just enter the pink expression into your calculator. So again, this is where calculators come in handy. You can probably enter this entire expression into this expression here. It'll take some time, and I know it's kind of tedious to do that, but sometimes you come across these problems. So if you do that, this first value, you get approximately 3.4641, and that's obviously positive. So what does that mean? It means there's a local minimum at x equals 4 plus root 1 over 27. Okay, and let's see what happens if you plug in the negative version of that. I'm doing this on my calculator, and I get negative 3.4641. So that's obviously negative. So the second derivative test tells us that there's a local maximum at x equals 4 minus the square root of 1 over 27. So there you go. So we had these two numbers that were critical numbers, and we tested those in the function, the second derivative function. If we test x equals 4, then obviously the second derivative is undefined, and that leads us to saying that that it's undetermined whether or not the function has a maximum or minimum value at x equals 4. So I'm going to give you another chance to take a picture of the second derivative test, and I want you to get a picture of all the problems that we just did. Here's problem number 11 and 12. And again, you don't have to use the first derivative test if the second derivative test doesn't work, because it takes away the focus from what we're doing today. Here's a picture of the number 13, and here's a picture of number 14. And I want you to try number 15. So again, what we're doing here is we're trying to find where the maximum and minimum values of this blue function up here occur. We're trying to find the location, and we're trying to identify each location as the location of a maximum or a minimum. And if the second derivative test doesn't tell you anything, you have to say that it's undetermined at whatever x value didn't work in the test. So try number 15. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, I want you to try number 16. Again, we're looking for the locations of the maxima and minima, and we want to differentiate between the locations of maxima and the locations of minima. Try number 16. When you come back, we'll do it together. Okay, we're back. And we don't know if there's a local maximum or minimum. But we'd have to do further work to figure that out. So again, you don't have to use the first derivative test. If the second derivative test fails, you would then have to go to the first derivative test. But that just takes away time from this class. You can do that if you want, but I don't know if we're gonna have time for that. So if you got that right, excellent. Go ahead and take a picture of these two problems. And now I want you to try number 17. Now, on number 17, we have an expression of the form ax to the fourth plus bx squared plus c. Remember that? Sometimes in calculus, you're going to see these expressions. So you have to know how to factor those. So if you get stuck with that, that's okay. But attempt this problem and see what you can do. You're also going to have to factor the difference of two squares. For example, you might have like x squared minus 81 or x squared minus 100. That's x minus 9 times x plus 9. So you're going to have to do all that math. That's the type of math we learned in previous classes. So try number 17. When you come back, we'll do it together. Okay, we're back. So if you got those right, excellent. Good job. Go ahead and take a picture of this problem and use it to help you with the last problem where we're going to use the second derivative test in this class. So again, we're looking for the locations of maxima and minima, and we want to know what locations lead us to a maximum and what locations lead us to a minimum. So try number 18. When you come back, we'll do it together. Okay, we're back. So if you got that right, good job. So now we're going to learn concavity and inflection points. These are things that are related to the second derivative. If the second derivative is positive on some interval, then the graph of the corresponding function is what we describe as concave upward. And if the second derivative is negative on some interval, then the graph of the corresponding function is what we describe as concave downward on that interval. So here's an example. The purple parts of this graph are concave downward and the blue part is concave upward. Now, the idea of concavity is pretty easy to understand, but it's not so easy to explain. But if you had to explain it, we could say that maybe there is a cliff and the ground is down here, and let's say that we want to create a cave, so we dig into the side of the cliff. If we dig into the side, then we're probably going to create something that we would describe as this part of the cliff would be described as concave. And whatever forces create that cave would have to come from out here, whether it be wind or water or digging with a shovel. So that's why we call that shape concave. Now, why is the purple part concave down and the blue part concave up? Well, if you were going to carve out a shape like this, you would probably have to be standing below the graph. So because you're below the graph, that might be one reason to call it concave down, even though you'd be carving up. And on this part of the graph here, you'd have to stand above the graph to carve out that shape. So because you're above the graph, we could say it's concave up. That's one way to remember it, but again, it's not easy to explain these concepts, even though they're fairly simple to understand. Now remember, if a parabola looks like this, then we say the parabola opens up. And it turns out that this parabola is concave up everywhere. So that's another way you can think of it. A parabola that looks like this, we say it opens down, and it turns out that it's concave downward also. So that's another way of thinking about it. Now, another way to think of concavity is whenever the lines that are tangent to a graph are above the graph. See how the blue line is above the red graph? On that part of the graph, the concavity is downward. If you move the point over here and make your line, again, the graph is below the tangent line, so that's a part of the graph that is concave downward. But if we draw a line tangent to the graph on the blue part of the function, then you can see that the red graph is actually above the tangent line. That's because in the blue part, the concavity is it's upward concavity. So that's just another way to think about it. Again, concavity is easy to understand, but not so easy to explain. Now, where the concavity changes, we call those inflection points. Now, as we said, the second derivative is negative when a graph is concave downward. Now, remember, the first derivative is the slope of the tangent lines. So the slope of that blue line is the first derivative. The second derivative is how fast the slope of the blue line is changing. Now you tell me, isn't it true that as your point goes to the right, the slope of the tangent line is getting smaller and smaller? It's decreasing. Over here it's positive, then it turns to negative, and it turns to a bigger negative number. So the slope is actually decreasing. So that means that the second derivative is going to be negative. That's one way to think about it. But then when we get over here, look what happens to the slope of the tangent lines. That slope is negative, right? But this slope is also negative, but it's not so negative. It's a bigger number. Then over here, the slope is positive. So you can see that the slope of the lines tangent to the graph are actually increasing. So that's why when the second derivative is positive, you have a concave upward graph. Again, the second derivative is how fast the slope of the tangent line is changing. So the slope of the tangent line is how fast the y values of the graph are changing as the x values change. But the second derivative is how fast the rate of change of the y values is changing as the x values increase. So I know it's kind of complicated to think about that, but now the inflection points are where the second derivative is going to be 0, because if your derivative, the slope of the tangent line is decreasing, that means the second derivative is negative, but all of a sudden here you can see that the slope actually starts to increase. So the second derivative would be negative here, but positive here, as we just described, but that means that at some point it has to change sign, which means that the second derivative is going to be 0. So we have the definition of an inflection point. It's a point on the graph of a function where the second derivative changes sign. And we have a theorem that is the second derivative version of Fermat's theorem. Remember, Fermat's theorem tells us that if you're trying to find, it tells us if you have a maximum value or a minimum value, then the derivative at that location is going to be either 0 or it's not going to exist. That's the first derivative version of this. But the second derivative version says kind of the same thing, but except with the second derivative. If you have a point we know is an inflection point, then that means that the second derivative at that location is going to be 0, or the function is not going to be differentiable at x equals a. So very similar to Fermat's theorem. So now it's time to do some practice problems. So we're going to find the intervals of concavity of the functions below, and we're also going to find the location of any inflection points. So concavity is determined by the second derivative, so we have to find the second derivative, but we can't find the second derivative unless we first find the first derivative. So do you agree with that? Did I do that right? It looks right to me. So now let's find the second derivative. So that is the second derivative. And now what we have to do is make a sign chart and figure out where the second derivative is positive and where it's negative. If the second derivative is positive, then in that part of the function, the graph is concave upward. And if the second derivative is negative, the graph is concave downward. And if the second derivative changes sign at some x value, then that's the location of an inflection point. Okay, so where does the graph change sign, or where does the double derivative change sign? Well, obviously where the double derivative is 0. So that's the special point where things change. So I'm going to set this expression equal to 0, and I'm going to factor out -1. You don't have to factor out -1, but it makes it a lot easier to solve. And what two numbers multiply to 6? And what two numbers multiply to 8? I'm going to try -1 and +8. And looks like we get +13, so I have to change those signs. Okay. So now we can solve. And now we're ready to write our sign chart. So again, those are the x values where the second derivative is 0. So now we're going to find the sign By the way, it's the same thing as 2 2/3. So we're going to find the sign of the second derivative in all these regions. We're going to test the blue region, the purple region, and the orange region. So let's try -1. That's the blue region. And we can plug in -1 to any one of these expressions here, whichever is easier. And if you're going to do this in your head, I feel like this expression would be easiest. But just to simplify things, I'm going to use this expression here. So we're going to plug in -1. So I think I got that right. We plugged in -1 to this function here. And I guess I can rewrite that whole thing above our sign chart, just so we have it right in front of us. There we go. So let's see what we get here. Looks like we have -6 minus 13 plus 8. That equals -11, which is a negative number. So I'll put a negative up there. And then we're going to evaluate the second derivative at 0 is probably the easiest number to use, right, for the purple. So plug it in 0. And I just want to make it clear that you don't have to show this math that I'm showing here. All you have to do is show that you're finding this and you're finding the answer that's negative. You don't have to show all that. The only reason we're showing all that is just so you can go back and look at what we're doing with your notes, and it'll be a guide for you. So it looks like we get +8. So obviously that's a positive number. And I think 3 would be a good number for the orange region. Looks like we get -54 plus 39 plus 8, and that's equal to, looks like -7. So obviously that is negative. And let's just double check that. Everything looks right. Okay, so we now know the sign of the second derivative in those regions, and these x values are the only x values where the second derivative can change sign. There's no other places, because this function up here is not going to be undefined anywhere because it's a polynomial. We're not going to have any problems with 0 in denominators, or negative numbers in roots, or negative numbers in logarithms, or anything like that. So now we can figure out where the whole point of this is to figure out where the graph of this corresponding function is concave upward and concave downward, and so on and so forth. So we know the graph is concave upward from -1/2 to 2 2/3. We know the graph is concave downward from negative infinity to negative 1/2, or 2 2/3 to infinity. Okay, and we have inflection points. Well, remember, the inflection points occur when the second derivative changes sign. So the inflection points occur at x is equal to negative 1/2, because the second derivative changes from negative to positive there, right? And 2 2/3, because the second derivative changes from positive to negative there. So that's it. That's all you have to do. As you can tell, this is really not that difficult. So let's try another one of these. You can get a picture of this information if you want. Okay, so we're going to find the intervals of concavity and the locations of the inflection points. So concavity is determined by the second derivative. So before we do that, we have to find the first derivative. And before we find the first derivative, we have to rewrite this in a form that is easier for us to analyze, and that's exponential form. Then we can find the first derivative. And we would have to use the chain rule, but the derivative of the inside is just 1. So, okay, so now we're going to find the second derivative. And so we're going to bring this down and multiply it into that, and we get negative 6 over 25. Subtract 1 from the exponent, and we get negative 8 over 5. And now we have to change this into something that makes sense. So this is going to be negative 6 over 25 times the 5th root of x minus 1 to the 8th power. Okay. So now we have the second derivative, and we can do a sign chart. But we want to find where the second derivative is 0, because remember, the sign of the second derivative changes, or it could potentially change where the second derivative is 0. That's what we found up here. And again, that's the inflection point theorem. So you see the green 0, we set it to 0, we found those values. That's just where the second derivative could possibly change sign. Problem is, we can't make the second derivative equal to 0. It's impossible for this expression to be equal to 0. If it were equal to 0 somewhere, then there would be an x in the numerator, but there isn't. But there is an x value that makes this function not differentiable. Remember, the inflection point theorem tells us that if x equals a is the location of an inflection point, then either the second derivative is equal to 0 at that x value, or the original function is not differentiable at x equals a. But look at the first derivative. Let's write the first derivative in a form that we can understand, and you can see that the first derivative is undefined when x is equal to 1. So I'm going to write over here, x cannot be equal to 1. because we get 0 in the denominator. I'm going to write that a little better. I know it's tempting to not write legibly, but in math we really can't do that. You have to write legibly, or don't write at all. Okay, so yes, we can't. The function is not differentiable at x equals 1. So that's a potential place where the where we could have an inflection point. Okay, so I'll put inflection point with a question mark. And now we need to do a sine chart. So we're going to check the sine of the second derivative. So I'm going to mark 1 here. And let's test this blue region over here, and then we'll test the purple region. So let's test the second derivative at 0 is a good point to choose. And if we plug in 0, we have 6 over, actually negative 6. Negative 6 over 25 times the 5th root of 0 minus 1 to the 8th power. And then we get negative 6 over 25 times the 5th root of negative 1 to the 8th power. We don't really have to show all the steps. Negative 1 to the 8th power is just positive 1. And the 5th root of positive 1 is just 1. So we end up with negative 6 over 25. So I'm not trying to rush through that to be annoying, but we don't really have a lot of room. So just do this orange part first, then raise to the 8th power, then the 5th root of that, and we end up with negative 6 over 25. So obviously that is a negative number. So we tested the blue region. Now we just need to test the purple region. So now what should we plug in? Maybe 2. And again, this is really tedious to have to show this, so you don't have to show all this. I don't know why I wrote a 0 there. That should be a 2. So we end up with negative 6 over 25 again. So notice that the sign of the second derivative did not change. That means that is not the location of an inflection point. So the graph is concave. It's concave downward everywhere, basically, except 1. It can't be concave down or up at 1 because the second derivative is not even defined at 1, right? So in green over here, I'm going to put x cannot be equal to 1 for this equation either. The second derivative just is not defined there. So the graph is concave downward from negative infinity to 1, or 1 to positive infinity, but not at 1. And there's no inflection points, and there's no upward concavity. So I want you to get a picture of this here, and I want you to get a, well, you can just use number 20, I'll keep that in the window, and I want you to try number 21. So you're going to find the intervals of concavity and the locations of the inflection points. So locations would be just, the x values where the sign of the second derivative changes. So try number 21, and when you come back we'll do it together. Okay, we're back. So if you got these answers, good job. Okay, so I'm going to give you one more chance to take a picture of this information here. And I don't know why, but I guess I forgot to rectangle these. Forgot to rectangle these too. So get a picture of this, what we just did, and I want you to try one more of those problems. We're looking for the intervals of concavity and the locations of the inflection points. So try 22. When you come back, we'll do it together. Alright, we're back. Okay, so if we compare that to this one over here, notice that there was no inflection point, and that's because the sign didn't change. But over here, this is the sign of the second derivative change, so we had an inflection point at x equals 0. So if you got that right, good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, all of the differentiation formulas, and screenshot number 2, and number 3, and number 4, and number 5, 6, 7, 8, 9, and 10. And 11, 12, and 13. But don't go before you get your homework. Let's take a look at the homework. Here's screenshot number 1 of the homework, and number 2, number 3, number 4, number 5, number 6, and here's the answers to the homework. Remember, it's not enough just to attempt the homework, it must be done correctly, so check all of your answers for every problem, and if you do it incorrectly, go back and figure out what you did wrong. You must have all the correct work and all the correct answers, so get that homework done, and I'll look forward to seeing you in the next class.